Let us begin with several questions that sit at the boundary between physics and philosophy, questions that have puzzled scientists since the early 20th century, when Niels Bohr, Werner Heisenberg, and their colleagues at the Institute for Theoretical Physics in Copenhagen first grappled with the strange implications of quantum mechanics. As we explore these questions, you'll see animated diagrams illustrating the conceptual landscape we're navigating. How can two particles separated by light years exhibit correlated behaviors instantly? This puzzle, first articulated by Albert Einstein, Boris Podolsky, and Nathan Rosen in their famous 1935 EPR paper, challenged the completeness of quantum theory. Einstein called this spooky action at a distance, a phrase that captured his deep discomfort with non-local correlations. Moving graphics now demonstrate this correlation across vast distances. Is the universe fundamentally local, or could non-local connections be woven into its structure? This question divided the physics community for decades. Einstein insisted on locality, the principle that objects are only influenced by their immediate surroundings. Yet quantum mechanics, as developed by Erwin Schrödinger, Paul Dirac, and others, suggested otherwise. Animated visualizations are now showing the contrast between local and non-local frameworks. What does quantum entanglement reveal about the nature of information, measurement, and reality? Erwin Schrödinger, who coined the term Verschränkung, entanglement, in 1935, called it the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. John Bell's 1964 theorem later provided a mathematical framework to test these ideas experimentally. You're now viewing motion graphics that illustrate the flow of quantum information. To frame these questions, consider the following scenario: a thought experiment refined over decades by physicists, including David Bohm, who in 1951 reformulated the EPR paradox using spin measurements rather than position and momentum. This reformulation made the paradox more experimentally accessible. Animated sequences are now being displayed to set up this scenario. Imagine two particles created together in a single quantum event, perhaps through spontaneous parametric down-conversion, a process discovered in the 1960s where a single photon splits into two entangled photons. You send one to the far side of the galaxy and keep the other here on Earth. When you measure one particle's state, the other responds immediately, without any signal passing between them. This scenario, tested in increasingly sophisticated forms by Alain Aspect in the 1980s, Anton Zeilinger in the 1990s and 2000s, and many others, consistently confirms quantum predictions. How is this possible? Moving images now illustrate this galactic-scale thought experiment. Defining quantum entanglement. Quantum entanglement arises when two or more particles share a single unified quantum state, a concept that emerged from the mathematical formalism developed by John von Neumann in his 1932 treatise, Mathematical Foundations of Quantum Mechanics. In such systems, the state of each particle is not independent. Instead, the particles must be described collectively through what mathematicians call a tensor product space. Schrödinger emphasized in his 1935 papers that this non-separability represents the most profound departure from classical physics. You're now seeing animated representations of entangled quantum states evolving in Hilbert space. Key features, identified through decades of theoretical development by physicists including Eugene Wigner, John von Neumann, and later John Bell. Non-separability, the wave function describing the particles, cannot be factorized into individual components. This mathematical property, rigorously formalized in the 1930s and 1940s, means the quantum state exists as an irreducible whole. Von Neumann's density matrix formalism, introduced in 1927, provides the mathematical tools to describe such non-separable states. Moving visualizations now show the mathematical structure of non-separable wave functions. Instantaneous correlations, Measurement of one particle's property, such as spin orientation along any chosen axis, defines the outcome of the corresponding property in the other particle, regardless of separation distance. This correlation structure was precisely characterized by David Bohm in 1951 using spin-half particles, making the phenomenon more experimentally tractable than Einstein's original position momentum formulation. Animated sequences are now demonstrating these instantaneous correlations across space. No transfer of usable information. Faster than light. Although correlations appear instantaneous, they cannot be used to send meaningful signals faster than light, a constraint proven mathematically by Philippe Eberhard in 1978 and independently by Asher Paris and others. This no signaling theorem ensures compatibility with special relativity, addressing Einstein's concerns about causality. Relativity remains intact. You're now viewing motion graphics illustrating why superluminal communication remains impossible despite instantaneous correlations. An analogy, technically imperfect but useful for building intuition, though as Niels Bohr often warned, classical analogies inevitably fail to capture quantum reality fully. Think of two coins minted as a special pair. When flipped, they always land on opposite sides. The correlation is built into the pair from the moment of their creation, not transmitted later by any signal. However, unlike classical coins, quantum particles exist in superposition until measured, as demonstrated in countless experiments from the double-slit experiment first performed by Thomas Young in 1801 to modern quantum erasure experiments. Animated coin flip sequences are now being shown to illustrate this classical analogy. Quantum mechanics formalizes this through coherent superposition and shared wave functions, mathematical structures developed in the 1920s by Schrödinger, Heisenberg, Dirac, and others. The formalism of entangled states was further refined by David Bohm, Yakir Aharonov, and later by researchers developing quantum information theory in the 1990s. Moving visualizations now display the mathematical representation of superposition and entangled wave functions. 3. Experimental verification. Entanglement is no longer theoretical speculation. Since the 1970s, laboratory experiments have confirmed its existence repeatedly, especially through tests of Bell's inequalities, which distinguish classical physics from quantum predictions. John Bell's 1964 theorem, published in the obscure journal Physics Physique Physica, went largely unnoticed until the early 1970s when John Clauser, Michael Horn, Abner Shimoni, and Richard Holt, CHSH, reformulated it into an experimentally testable form. Their 1969 paper provided the foundation for all subsequent experimental tests. Animated timelines and experimental setups are now being displayed. Key milestones in the experimental verification of quantum entanglement. Aspect experiment, 1982. Alain Aspect and his team at the Institute of Optics in Orsay, France, performed the first convincing violation of Bell's inequality using photons from calcium cascade decay. Their experiment employed rapidly switching analyzers to address the locality loophole, achieving results that deviated from classical predictions by more than 40 standard deviations. This work built directly on Clauser and Friedman's 1972 experiment, but with crucial improvements in timing and detector efficiency. Moving images now show the Aspect experimental apparatus and results. Loophole-free Bell tests, 2015. 3 independent experiments by Ronald Hansen's group in Delft using electron spins and diamond, Anton Zeilinger's group in Vienna using photons, and Lyndon Shalm's team at NIST in Boulder, simultaneously closed major experimental loopholes, including the detection loophole and locality loophole. These experiments, published in Nature and Physical Review letters, strongly favored quantum non-locality over any local realistic theory. Animated graphics are now displaying the 3 experimental configurations and their combined significance. 2024 advances representing the cutting edge of experimental quantum physics. Entanglement distributed over increasing distances using quantum satellites. Building on China's MISHA satellite launched in 2016 by Janwei Pan's team, which demonstrated entanglement distribution over 1,200 kilometers. Recent advances have extended these distances and improved fidelity, with European and American satellite programs now in development. You're now seeing animated satellite trajectories and entanglement distribution patterns, improved entanglement fidelity in multi-photon systems, with experiments now routinely creating and manipulating entangled states of 10 or more photons, far beyond the two-photon experiments of the 1980s and 1990s. These advances, pioneered by groups including Jianwei Pan's laboratory in China and Anton Zeilinger's group in Austria, enable more complex quantum information protocols. Moving visualizations now illustrate multi-photon entangled states. Progress toward entangling mesoscopic objects containing thousands to millions of atoms. Experiments by Marcus Aspelmeyer's group in Vienna, among others, have demonstrated quantum effects in increasingly massive systems, including micromechanical oscillators and levitated nanoparticles. These experiments probe the boundary between quantum and classical physics, testing whether quantum mechanics applies universally or breaks down at some scale. Animated sequences are now showing these mesoscopic quantum systems. The empirical evidence is overwhelming. Entanglement is real and ubiquitous, a conclusion that would have astonished Einstein, who died in 1955 believing quantum mechanics was incomplete. The 2022 Nobel Prize in Physics, awarded to Alain Aspect, John Clauser, and Anton Zeilinger, recognized their pioneering experimental work establishing entanglement as physical reality. Moving graphics now summarize the cumulative experimental evidence. IV applications from theory to technology. What was once an odd theoretical feature, dismissed by some as mere philosophy, is now driving emerging technologies with potential economic impact in the trillions of dollars. This transformation began in the 1980s and 1990s with the development of quantum information theory by Charles Bennett, Gilles Broussard, Arthur Eckert, and others who recognized that quantum properties could be harnessed for practical purposes. Animated graphics are now displaying the transition from theory to technology. 1. Quantum communication. Entangled photons enable quantum key distribution, QKD, a method for unhackable encryption first proposed by Charles Bennett and Gilles Broussard in 1984, the BB84 protocol, and enhanced by Arthur Eckert in 1991 using entanglement. Any attempt to intercept the photons modifies their state, revealing the intrusion, a consequence of the quantum no-cloning theorem proven by William Wouters and Wojciech Zurek in 1982. Commercial QKD systems are now deployed by companies including ID Quantique, Toshiba, and Quantum C-Tech. You're now seeing animated demonstrations of quantum key distribution protocols and eavesdropping detection. Several countries have already launched quantum encrypted satellite links spanning hundreds of kilometers. China's quantum communication network, anchored by the Missius satellite and ground-based fiber networks, now extends over 4,600 kilometers. The European Quantum Communication Infrastructure, EuroQCI initiative, launched in 2019, aims to create a continent-wide quantum network by 2027. Moving images now show the global quantum communication infrastructure under development. 2. Quantum computing. Quantum processors from IBM, Google, and others employ entanglement to link qubits into computational networks. The development of quantum computing traces back to Richard Feynman's 1981 proposal that quantum systems could simulate other quantum systems more efficiently than classical computers, and David Deutsch's 1985 formulation of the universal quantum computer. In 1994, Peter Shor at Bell Labs discovered his famous factorization algorithm, demonstrating that a quantum computer could break RSA encryption exponentially faster than classical methods. Love Grover followed in 1996 with his search algorithm, providing quadratic speedup for unstructured search problems. Today, IBM's quantum processors have scaled to over 400 qubits, while Google achieved quantum supremacy in 2019 with their Sycamore processor, performing a calculation in 200 seconds that would take classical supercomputers thousands of years. These systems fundamentally rely on entanglement to create correlations between qubits that enable parallel quantum computation. Moving images are now being shown illustrating the architecture of quantum processors and the entanglement networks that link qubits together. This represents the practical realization of decades of theoretical work. 3. Quantum sensing. Entangled systems improve measurement precision beyond classical limits, a boundary known as the Heisenberg limit, named after Werner Heisenberg's 1927 uncertainty principle. The theoretical foundation for quantum-enhanced sensing was laid by Carlton Caves in 1981, who showed that squeezed light could improve interferometric measurements. In the 1990s, researchers, including Jeffrey Kimball and Anton Zeilinger, demonstrated that entangled photon pairs could achieve sub-shot noise sensitivity. The field has since expanded dramatically. Applications now include ultra-sensitive magnetic field detection, pioneered by groups at MIT and Berkeley for detecting neural activity and geological surveys. Advanced medical imaging techniques using entangled photons can reduce radiation exposure while improving resolution. The LIGO gravitational wave detectors, which made their historic first detection in 2015, are being upgraded with quantum-enhanced techniques using squeezed light to push beyond the standard quantum limit. Moving animations are being displayed showing how entangled particles enable measurements that surpass classical precision boundaries, visualizing the quantum advantage in sensing applications. These technologies demonstrate entanglement's transition from theoretical curiosity to practical engineering tool. Quantum sensing represents one of the nearest term applications of quantum technology. The precision gains are not incremental, but represent fundamental improvements in our ability to measure physical phenomena. Entanglement is transitioning from laboratory oddity to engineering tool, with commercial quantum sensors already entering the market. Implications for our understanding of reality. Entanglement forces us to reevaluate foundational assumptions about the nature of physical reality itself. 1. Locality. Albert Einstein, along with Boris Podolsky and Nathan Rosen, published their famous EPR paper in 1935, arguing that quantum mechanics must be incomplete because it predicted what Einstein called spooky action at a distance. Einstein firmly believed that no influence can travel faster than light, a principle central to his theory of relativity. He proposed that hidden variables must exist to explain quantum correlations without violating locality. Niels Bohr immediately responded, defending quantum mechanics' completeness, initiating one of physics' greatest debates. The question remained philosophical until 1964, when John Stuart Bell, working at CERN, derived his famous inequalities. Bell's theorem provided a mathematical test. Any local hidden variable theory must satisfy certain statistical bounds, while quantum mechanics predicts violations of these bounds. Beginning with Alain Aspect's groundbreaking experiments in 1982 at the Institut d'Optique in Paris, and culminating in the loophole-free tests of 2015 by groups in Delft, Vienna, and Boulder, experiments have consistently violated Bell's inequalities. Moving visuals are being shown depicting the EPR thought experiment, Bell's inequality tests, and the experimental setups that confirm quantum non-locality. The evidence is conclusive. Any theory preserving classical notions of both locality and realism cannot reproduce experimental results. We must abandon at least one of these deeply intuitive assumptions about reality. 2. Reality and measurement. The measurement problem in quantum mechanics has troubled physicists since the theory's inception. John von Neumann formalized the issue in his 1932 Mathematical Foundations of Quantum Mechanics, describing the collapse of the wave function upon measurement. Erwin Schrödinger illustrated the paradox with his famous cat thought experiment in 1935, showing how quantum superposition, when extended to macroscopic objects, leads to seemingly absurd conclusions. Entangled systems amplify this puzzle. They do not possess definite properties prior to measurement. Instead, outcomes are defined during the act of measurement itself. When you measure one particle in an entangled pair, you instantaneously affect the quantum state of the entire system, regardless of spatial separation. This was demonstrated experimentally by Aspect and refined in countless subsequent experiments. The act of measurement is not passive observation, but active participation in defining reality. Animated diagrams are now being displayed showing the measurement process, wave function collapse, and how measuring one entangled particle instantaneously affects its partner. 3. A deeper connectivity. Multiple interpretations have been proposed to explain entanglement's implications, each with distinguished proponents and unique philosophical commitments. The Copenhagen interpretation, formulated primarily by Niels Bohr and Werner Heisenberg in the 1920s, holds that quantum probabilities collapse upon measurement, with the wave function representing our knowledge rather than physical reality. This remains the most widely taught interpretation, though it leaves the mechanism of collapse unexplained. Moving graphics illustrate the Copenhagen view of wave function collapse. The many worlds interpretation proposed by Hugh Everett III in his 1957 Princeton dissertation eliminates wave function collapse entirely. Instead, all possible measurement outcomes exist simultaneously in branching parallel universes. When you measure an entangled particle, the universe splits into multiple branches, each containing a different outcome. This interpretation, championed later by Bryce DeWitt and David Deutsch, preserves determinism but at the cost of an infinity of parallel realities. Animations are being shown depicting the branching structure of the many worlds interpretation. Pilot wave theory, or Bohmian mechanics, was originally proposed by Louis de Broglie in 1927 and rediscovered by David Bohm in 1952. This interpretation posits that particles have definite positions at all times, guided by a non-local pilot wave. Hidden variables exist, but they operate through instantaneous non-local connections. While deterministic and ontologically clear, it requires accepting explicit non-locality. Visual representations are being displayed showing pilot waves guiding particle trajectories. The quantum information perspective, developed by researchers including Charles Bennett, Gilles Bressard, and others since the 1980s, views entanglement as reflecting shared information rather than physical signals. In this view, pioneered by John Wheeler's it from bit philosophy, information is fundamental, and entanglement represents correlations in the information structure of reality. This approach has proven particularly fruitful for quantum computing and cryptography. Moving diagrams illustrate information theoretic representations of entanglement. Regardless of which interpretation one favors, entanglement implies an underlying interconnectedness in the quantum domain that defies classical intuition. The universe, at its most fundamental level, appears to be woven from relationships rather than isolated objects. Future directions. What's next for quantum science? One, larger scale entanglement. Physicists are attempting to entangle increasingly massive systems, pushing the boundaries between quantum and classical regimes. Marcus Aspelmeyer's group in Vienna has entangled nanomechanical oscillators containing billions of atoms. In 2022, researchers at Delft University successfully entangled 2 diamond crystals separated by 1.5 kilometers. Groups at MIT, Caltech, and the University of Vienna are working to entangle objects visible to the naked eye. The goal is to test whether quantum mechanics applies without modification to macroscopic systems, or whether new physics emerges at larger scales, as some theories of quantum gravity predict. These experiments probe the boundary where quantum mechanics meets general relativity. Moving footage is being shown of laboratory setups attempting to create and verify macroscopic entanglement. Successful large-scale entanglement could bridge the gap between quantum and classical worlds, potentially revealing new physics at the mesoscopic scale and testing the limits of quantum theory itself. 2. Quantum biology, speculative but active research. There are hypotheses, still unproven but under active investigation, that quantum processes, including entanglement, may play functional roles in biological systems. In 2000, Thorsten Ritz proposed that European robins use quantum entanglement in cryptochrome proteins for magnetic field detection during migration. Graham Fleming's group at Berkeley discovered in 2007 that photosynthetic complexes exhibit quantum coherence at room temperature, suggesting quantum effects in energy transfer. Luca Turin has proposed quantum tunneling mechanisms for olfaction. Most speculatively, Roger Penrose and Stuart Hameroff have suggested quantum processes in microtubules might be relevant to consciousness, though this remains highly controversial. Matthew Fisher at UC Santa Barbara has proposed that nuclear spins of phosphorus atoms in Posner molecules could maintain quantum coherence in the brain. While most of these ideas remain speculative and face significant skepticism, they represent an exciting frontier. Animations are being displayed showing proposed quantum mechanisms in biological systems. These investigations span avian navigation, photosynthetic efficiency, olfactory discrimination, and potentially neural processing. The challenge is demonstrating that quantum effects are not merely present, but functionally relevant in warm, wet, noisy biological environments. This remains one of the most controversial and exciting areas of quantum research. If confirmed, it would suggest that evolution has learned to exploit quantum phenomena for biological advantage, fundamentally changing our understanding of life itself. 3. Quantum gravity and cosmology. Some researchers propose that space-time itself may emerge from entanglement patterns, suggesting that geometry arises from information. This radical idea originates from black hole thermodynamics, developed by Jacob Bekenstein and Stephen Hawking in the 1970s, which revealed deep connections between gravity, entropy, and information. Juan Maldacena's 1997 ADS-CFT correspondence demonstrated that a gravitational theory in a higher dimensional space is mathematically equivalent to a quantum field theory without gravity on its boundary. Mark van Ramsdonk showed in 2010 that entanglement in the boundary theory corresponds to geometric connectivity in the bulk spacetime. This suggests that the fabric of spacetime itself is woven from quantum entanglement. Leonard Susskind has called this ER equals EPR, proposing that Einstein-Rosen bridges, wormholes, and Einstein-Podolsky-Rosen pairs, entanglement, are manifestations of the same phenomenon. Moving visualizations are being shown depicting how space-time geometry might emerge from patterns of quantum entanglement. This radical idea, rooted in theoretical frameworks such as holography, tensor networks, and the ADS-CFT correspondence, hints that the universe's structure at its deepest level may be an entanglement network. Space and time may not be fundamental but emergent properties of quantum information. If true, this would represent the most profound shift in our understanding of reality since Einstein's relativity. 7. Conclusion: the universe as an interconnected system. Quantum entanglement challenges the classical assumption inherited from Newton and reinforced by our everyday experience, that objects are fundamentally separate and independent entities interacting only through local forces. Instead, the accumulated evidence from nearly a century of quantum mechanics suggests a radically different picture. The universe may be woven from relationships rather than isolated parts. Objects do not possess intrinsic properties independent of their connections to other objects. Information, correlation, and connection lie at the heart of physical law. What we call particles may be better understood as nodes in a vast network of quantum correlations. Separation in space does not necessarily imply separation in the underlying quantum reality. Two particles on opposite sides of the universe can remain fundamentally unified through their shared quantum state. As we continue exploring entanglement from subatomic particles to cosmic scales, from laboratory experiments to technological applications, We may uncover principles that unify physics, information theory, and perhaps even our understanding of consciousness and the nature of observation itself. The philosophical implications extend far beyond physics, touching on questions of determinism, causality, and the relationship between mind and matter that have occupied philosophers since antiquity. Moving imagery is being displayed, synthesizing the key concepts of quantum entanglement and its implications for our understanding of reality. In short, the universe may be far more deeply interconnected than our classical intuitions suggest, with entanglement revealing a fundamental unity beneath apparent separation.